this video on probability models, basic rules of probability. By the end of this video, you should be able to give the probability model for a chance process with equally likely outcomes and use it to find the probability of an event. You should also be able to use basic probability rules, including the complement rule and the addition rule for mutually exclusive events. So today we're going to talk about who will win the last banana. We're going to play a dice game. And so suppose you're on a desert island playing dice with another castaway. The winner's prize will be the last banana. Here are the rules of the game. Each player will roll a die. If the largest value shown is a 1, 2, 3, or 4, then player 1 wins. If the largest value is a 5 or a 6, then player 2 will win. And it doesn't matter who rolls the dice. It's all dependent on the number, not the person throwing it. So take a second, pause the video if you need to, decide if you're player 1 or 2. It's not really going to make a difference because I'm going to give you some data, but just to see what you, whether you're a big winner or not. Okay, so you should have made a decision here. What we did is we rolled the dice, and so here I have a 1 and a 2. That would be player 1 won because the largest number here. I got a 2 and 2, that's a player 1. A 3 and a 3, that's also player 1. So we would just keep rolling the dice 20 times and take a tally of how many times players won. So we have player 1 and 2. I played the game 20 times, and player 1 ended up winning 9 times. And player 2 then won 11 times. Okay, so our winning percentage, well, let's talk about these and we can go back there. So player 1 9 times, player 2 won 11 times. To find this as a proportion, you won 9 out of 20, which is 0.45. And player 2 won 11 out of 20, which is 0.55. And as percentages, 0.55 is 55%, and 0.45 is 45%. All right, so let's take a look. Who won more often? Maybe this was only true for your group or the data that we're using today. Let's see how the rest of the class did. So in collecting from the rest of the class, let me give you their information. In combining for the entire class, we had 109 out of the 310 rolls had player 1 winning. So that equaled 0.35 or 35%. So what I want you to do, pause the video and see if you can figure out the proportion of wins for the player 2 for the entire class. All right, so using subtraction, if you said 310 minus 109, we got 201 out of the 310, or 65% of the time player 2 won. So what we have here is what we just got done talking about is something called experimental probability. So all of these numbers that we got all came from us doing an actual example together, a simulation. So this is experimental probability. And so that comes from either actually playing a game for real or simulating a game. What did we get in a short run? Okay, one of the things, most of you can do this inherently. You understood it without me teaching you some statistics behind it. That if I wanted to find out how many player 2s won, I just needed to do some subtraction to get that number. In stats, we call this a complement. So the probability of player 2 winning is 1 minus the probability of player 1 winning. That's exactly what you did. Okay. The other thing that we could call this player 1 is really player not 2. Let's see, that says not 2. So in this case, it just means 1 because that's the only other option we have. So the little c means complement. You can have multiple options here, and we would just subtract all of them except for the one we were talking about to get what we were talking about for our complement. All right, so what I want you to do now is I want you to finish filling out this table so we can talk about it. And these are just our dice combinations. So this would be a 1 and a 2, this is a 1 and a 3, this would be a 2 and a 2, this would be a 4 and a 3. So go ahead and finish filling that out and come back to the video when you're done. All right, looking at question 4. Question 4 says determine the true probability of player 1 winning. We should list out all the possible roles, which is what we did here. And this box over here, we call this as a sample space. And what a sample space is a list of all the possible outcomes. All right, so in our sample space, we want to know the probability of player 1 winning. Well, remember, player 1 wins if the biggest number is a 1, a 2, a 3, or a 4. So what that means is any dice rolls in this section will result in a winner. All the pink ones are winners. So we have a 4x4 block of winners, so that means there's 16 winners out of, well, this is 6x6, so there's a total of 36 boxes here, 16 out of 36, which is 0.44, so we'll call it 44.4%. Okay, so this is what our sample space tells us. That is not what we actually got. And we're going to talk about that in just a minute. Which do you think is closer to the normal probability you found in 4A? So up here, the true probability, did you think was from the class data or from a small group data like we did with our data up here? We got actually pretty close. But in general, the class data should be better because it's a larger sample size. There are more games played. And if you remember the last video, we talked about how a larger sample size and many, many repetitions of something helps you approach its true probability. All right, so in our sample space, we can determine what we call theoretical probabilities. This is what it should be. So theoretical probability, and this is after many, 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 many repetitions. Many, many, many. Okay, so when we say flipping a coin has a 50% chance of head, that's after thousands and thousands and thousands of coin tosses that we got that 50%. That's the theory behind it, but if we just toss it 10 times, that's not guaranteed what's going to happen. So theoretically, this is what should happen. So if we look at this, I had to play this game at a stats professional development I went to, and they were like pushing us, quick, pick player 1, player 2, and I picked player 1 because it had 4 dice that would win and player 2 only had 2 dice that would win, and I wasn't, because they were rushing us, I wasn't really paying attention. Well, player 1 has a 16 out of 36 chance of winning, while player 2 has a 20 out of 36 chance of winning. So it's already heavier towards the player 2. That's a better choice. That doesn't mean player 2 will always win. It just means they're more likely to win. All right, so last video we talked about something called the law of large numbers. And that is what this is referring to. Larger sample size, law of large numbers, the closer it will approach its theoretical probability. And remember, short-term probability is unpredictable. We just played 20 games. That's not a lot. But if we played 20,000 games, we would probably approach this probability that we're seeing over here. All right, let's summarize this down some. The first takeaway I want you to have is a probability model. On the front, we did a sample space, not a probability model, because a probability model will show all possible outcomes and their probabilities. We only showed the outcomes, so it's a sample space on the front. Your probability model must add to 1. So when you add up all the probabilities, it must equal 1. And all of your probabilities have to be between 0 and 1. I have seen multiple choice questions that will have negative probabilities, so it will still add to 1 when you add up your probabilities, but one of the probabilities is negative, and that is not a valid probability model. You cannot have negative probability. So if we take a look in our Check Your Understanding, question 1 says, explain why this is a valid probability model. So here we have the outcomes possible and their probabilities. When you add up these probabilities, they equal 1. So the one thing we'll say is the probabilities add to 1. And then the other thing, when I look at them, all of these are between 0 and 1. So we'll mention that too. That makes it valid. All right, and now let's get the rest of this so you can finish out your Check Your Understanding.